Review chapter 4, find dy dx. So on the very first one, dy dx is equal to first times the derivative of the second, and then times 20x to the third, and then plus the second times the derivative of the first, which will be 12x squared. So you got to use the product rule for this, and then we have that factor cancels out with the 5, leaving 4. And then we would have 16 x to the 6th over x to the 4th, so x squared. And then plus 12 natural log of 5x to the 4th. So we can factor out a 4. And, oh, no, I forgot the x squared here. A 4x squared. So we get 4 plus 3 natural log of 5x to the 4th. And then on the next one, we have the product rule again. So dy dx equals first times derivative of the second, which will be 1 over 2 square root of 4x minus 1, but then times 4, and then plus the second times the derivative of the first. But we don't leave them as two separate fractions. We want to combine them. So this is equal to, we have 4x squared plus 2x times 4x minus 1. Oh, no. Let's back that up, because I can make this a little simpler. We can cancel the 4 and the 2. Make that a 2. So now we have 2x squared plus 2x times 4x minus 1. And that's all over the square root of 4x minus 1. On the second one, that's what you get when you do the common denominator. When you multiply by the square root of 4x minus 1. We have 2x squared plus 8x minus 8x squared minus 2x over square root of 4x minus 1. And then we have 10x squared minus 2x over square root of 4x minus 1. Well, product rule again. I guess I really like product rule. We have first times the derivative of the second, which is negative cosecant squared 3x, but then times 3. So first times derivative of the second plus the second times the derivative of the first, which is negative cosecant 3x, cotangent 3x, then times 3. And that's not a minus, it's a negative, that's times. We have 3 cosecant to the third of 3x, and then minus cosecant 3x cotangent squared 3x, and I'll put the 3 out front. We can factor out a 3 cosecant 3x. We get cosecant squared 3x minus, I'm taking the 3 out, looks like cotangent squared 3x. And, I missed the negative here. So that means if I took a negative out of here, that'll be a positive. There we go. So I got my negative straight now. Questions on that one? Cosecant minus cotangent would have been 1, by the way, but I knew that it doesn't. It should be plus. Try that again. There we go. The derivative of log, so we have dy dx equals 5 times 1 over x squared, natural log of 3, but then times 2x. So just, if it was log base 3 of x, it's 1 over x natural log of 3, but there's an x squared there, so that makes that x squared natural log of 3 times the derivative of the inside. We get 10 over x natural log of 3 for a final answer. So there's your derivative of a common log. Now this one, if you look at natural log and you move left 1, 2, 3, 4, there's your vertical asymptote, and then this is very roughly, that's what the graph looks like. The whole point being that this graph does not exist to the left of negative 4. So the domain of the derivative can't be to the left of negative 4 because the graph doesn't even exist over there. But f prime of x is equal to 1 over x plus 4. Now, if 1 over x plus 4 was all by itself, the domain would be negative infinity to negative 4 to infinity. But the graph doesn't exist over from negative infinity to negative 4. So the domain for this one is negative 4 to infinity. Oh. No, that was right. That was right. I was thinking of something else. That was right. Negative 4 to infinity. Oh, there it is. It kind of blends in. All right, very good. This one goes very quick. dy dx is equal to, it's 4 to the 3x times the natural log of 4. So that's just the derivative of really just 4 to the x, except you got the 3, and then times 3. And I guess the one thing I could mention here is don't make that 12 to the 3x. That makes no sense whatsoever. So you can't multiply those. Thanks for letting me know. So there's your derivative of just an exponential function. Find the derivative. I'm going to show you two ways. The original way I showed, and then the new way, and then whatever you do on the test is up to you. But the derivative of inverse tangent is equal to 1 over 1 plus this thing squared, which is x squared over 16, but then times the derivative of the inside, which is 1/4. Now I can't have complex fractions, so that's 16 over 16 plus x squared times 1/4. So in other words, you multiply everybody by 16. That gets rid of the complex fraction. And then 16 divided by 4 is 4. We get 4 over 16 plus x squared. So that's the way I originally showed it. And then a couple of days ago, I went on the interwebs, and I found what I think is not a better way. It's just another way. But the one thing I like about this, the new way I'm showing you, is you don't have to memorize any formulas. The concept is, well, we take the tangent of both sides. So you get tangent of y equals x over 4. And then you say, well, if the tangent of y is x over 4, if I said that's y, that's the angle y, then opposite over adjacent is x and 4. And then this hypotenuse would be x squared plus 16, square root of x squared plus 16, just by Pythagorean theorem. If you take the derivative of both sides, secant squared y is equal to 1/4. Whoops, dy dx, because we're doing this implicitly. But secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So this is hypotenuse, hypotenuse over adjacent. So square root of x squared plus 16 over adjacent dy dx is equal to 1/4. Well, then you just multiply by the reciprocal. Oh, no, it's squared. Look at that, it's squared. So I'd have to square this. I'm like, why is this not going to work out? Dy dx equals 1/4, and then when you multiply by the reciprocal, you get to this spot right here. And so you end up with the exact same thing. Dy, didn't leave myself a whole lot of room, is 4 over x squared plus 16. So you get to the exact same spot, except you never have to memorize any formulas. If you just use trig, you got it. So on this one, I don't care which way you do it. If you've memorized the formula, it's going to be 1 over square root of 1 minus this thing squared, which is x, but then times 1 over 2 square root of x. But it's negative. I almost forgot the negative. So negative 1 over 2 square root of x, square root of 1 minus x. Questions on that? How about a parametric? This couldn't be any, if you remember what to do, everything's easy, right? But this one, I hope you remember what to do, because if you do, it's just so straightforward, I think. Not a whole lot of complicated calculations to be done here. Dy dx, or the derivative, is literally the derivative of y over the derivative of x. And then we're evaluating this when t equals 4. So we have 3 over 32. And that's all they wanted. Find dy dx as a function of t at the value. Done. Got it. Find the second derivative. F prime of x equals e to the x squared. The derivative of e is e. We love taking the derivative of e. Then times 2x. Then the second derivative, now we originally had one function. Now we have two functions. So it's first times the derivative of the second plus the second times the derivative of the first, which is still times that 2x. So we still do the chain rule. We can take out, what can we take out? A 2 and an e to the x squared. So that's 1 plus, see I took out, yeah I can't take out, I took one of these 2's out. So 2x squared, oh that's it, because I took out the e to the x squared. Now why you would want to do this is because we're going to try to find zeros of derivatives and zeros of second derivatives. Now I could find a zero even though in this case they'd be imaginary. But at least we know they're imaginary. So that's why we want to factor stuff out, because later we're going to be doing more stuff with it. Anything else? Oh yeah, a few more. Find the equation of the tangent line to the graph of that at the point 2, 1. So we have 2y dy dx minus 3 equals 0. Don't forget about taking the derivative of that other side, which will be 0. So dy dx equals 3 over 2y. So when we evaluate this at the point 2, 1, we only need the y. So it's 3 halves. Now here comes the easy part. Y minus 1 equals 3 halves times x minus 2. Actually write the equation of the tangent line. Follow the instructions, please. So don't stop at just finding the slope. And then this last one here, we have, suppose that functions f and g and their derivatives have the following values at x equals 2 and x equals 3. Evaluate the derivatives with respect to x of the following combinations at the given value of x. So we have this composition of functions right here. So this is like the chain rule. This is peeling the onion. We have the derivative of the outside, leave the inside alone, and then times the derivative of the inside. And all this is taking place at 2. So we're using the values up here. So f prime g of 2 is 2. And then g prime of 2 is negative 3. And then now I need f prime of 2, which is a third. So 1/3 times negative 3, we get negative 1. Over here we have the product of two functions. So we have first times the derivative of the second plus the second. Oh, wait, whoops. I didn't finish that. Shame, shame. Need the chain rule. So I did the power, but then I need a g prime of x there. So there's first times derivative of the second, all of that. And then plus the second times the derivative of the first. So that's the power rule, and then that's the derivative of what we would consider the inside function, g prime of x. So I didn't say where at, so how about x equals 2 again? So f of 2, hopefully these don't get too big. 8 times 3 times g of 2 is 2. I like that. That's not horrible, I guess. Times g prime of 2 is negative 3. That's going to be a big number. And then g to the third of 2. Yeah, so that's 8. And then times f prime of 2, which is 1/3. Negative 288. Plus 8/3, so times 3 plus 8. I get negative 856/3. On the test, I won't have anything that ugly. Find the 2 points where the curve x squared plus xy plus y squared equals 7 crosses the x-axis. Show the tangents to the curve at these points are parallel. What is the common slope of these tangents? Thank you. So we need the x-intercepts. So that's where y is 0. And they said there's 2 of them. So something comma 0 and something comma 0. Well, let's plug 0 in for y. We have x squared, equals 7. 0 here, 0 there. X equals plus or minus square root of 7. So these are the 2 points right here that they're talking about. Show that the tangent lines here are parallel. So that means derivative. we have 2x plus first times derivative of the second, plus the second times the derivative of the first, plus 2y dy dx, and that's equal to 0. Let's factor out a dy dx, and we get x plus 2y. That's equal to negative 2x minus y. And dy dx is now equal to negative 2x minus y over x plus 2y. So there's the derivative, but we have to show that the tangent lines at each of these points, they're parallel to each other. So we can evaluate this at negative, or square root of 7, 0. And what we get is negative 2 square root of 7 over square root of 7, because those y's will be 0. So the slope is negative 2 at positive square root of 7. And then dy dx evaluated at negative square root of 7, 0 is equal to negative 2 negative square root of 7 over negative square root of 7, which is a positive over negative, which is still negative 2. So we might say both slopes equal 2. So tangent lines are parallel. And then it says, well, what is the slope? And then our final answer is just, well, it's, negative 2. Final answer is negative 2 then.